Evening, everyone. Waiting for more of a turnout. Let's see here. Got no news from anything. Got the Padre and Dodger game going on right now. So, let's see.
Bobby,
remember, yep.
You might have already talked about this, but just in case you didn't, I just got an email from OCC. They want us to do some like meeting on Thursday. Do you know what that is?
I
just didn't know if that was like something. I doubt it's worth attending, so I normally delete those emails. But I just thought you.
Let me see.
Was.
I'll look at what I've got. Let's see. No. Let me see. No, that must have been a student email to the students.
Oh, okay.
I didn't get one. At least that I know of. I don't know. I just
like
looked on
an announcement about how they're going to run the school or something for the next semester. I just didn't know if it was worth. Probably it's not worth it. So I'm just curious.
Yeah, it's there we are from yesterday. I'm not so sure about anything anymore. You know, I mean, you get these people that test positive, like a bunch of people on the Cardinals tested positive. And there were a bunch of them were false positives. I'm not even gonna waste my time getting a test, you know.
I do it. I've heard it's a little bit painful too. So for the normal one where they stick the swab up your nose. My dad did it and it burned for like a day, but he's very old, so.
Yeah, I mean, I think I had it, you know, on top of everything else. So, okay, so today we are going to talk about Taylor's theorem. Okay, so this is why Brooke Taylor's name gets remembered. And turn some lights on in here. And you know, it's not for what we did yesterday. It's because of, you know, what he was able to establish. Okay, so let me find where I have all of this. I'm looking and I'm looking. Okay, so there it is. Okay, so here's the idea. We have a function, f of x. And it's a C infinity function on some interval, a minus r to a plus r. Okay, now the Taylor series for this f of x, let's call it t of x, okay? And it's going to be the sum from n equaling 0 to infinity, the nth derivative of x evaluated at a divided by n factorial x minus a to the nth power. Okay. And if we write out the first few terms of this, it's going to be, you know, f of a plus f prime of A times X minus A. And then it's going to be 1 over 2 factorial F double prime A X minus A squared. And if I go up to the nth one, it's going to be 1 over n factorial, the nth derivative evaluated at A, X minus A to the nth power. And then this keeps going and going and going. Okay, so here's the idea behind what we need to try to establish. So we let Tn be the usual thing, the nth Taylor polynomial. So it's going to be the sum k equaling 1, 0 to n. And then it's going to be the kth derivative now, evaluated at A, k factorial, x minus A to the counter. Okay. So this is the nth Taylor polynomial. Okay. Now, if we let's say Rn of x equal the function f of x minus Tn of x. That's what you want. You want to go outside? Go on. Go on. Okay. So this is going to be the difference between f of x and t of x, Tn of x. Okay. Now, we write down specifically what we want. We want a few things. Number one, we want f of x to equal this Taylor series. Okay. So if this is the difference right here between the two of these things, this would be equivalent to saying that if I took f of x minus Tn of x and Bellinger ground up equal to 0. Okay. So if we look at this, the magnitude of the difference between these two things is going to be the magnitude of this guy. Okay. And so if we can establish that the limit as n goes to infinity of this Rn of x in magnitude equaling 0, that is going to imply that f of x would actually equal its Taylor series. Okay. All right. So what Taylor figured out was kind of like a mean value theorem kind of an idea. Okay. So we'll just get right into it. Okay. So this is the theorem. Taylor. Not exactly sure what year he did this. I should probably dig around in some of my books. And yeah, we have superior notation. Taylor is the time of Newton. And so even, even in the mid 1500s, like in Riemann's paper of 1859, when he has a quantity t cubed, he'll write it t cubed. If he has a quantity t to the fourth. But in 1859, it was still customary to write t squared as t times t. So you read all of these old papers and you just like I tried to read the Principia once. That's Newton's classic work. It's written in English, and I had to get the translated version because of all the weird stuff he was saying and spelling stuff like choose, shoot in the Principia, choose,
I wonder if they didn't have standardized English at that point, so they just spelled it phonetically.
Maybe. So here's what we got. So let's suppose that we have this function f, and f is a Cn+1 function, means it's n+1 times differentiable on this open interval. Okay, and remember, you guys, you always need an open interval because of taking limits and so on and so forth. Okay, we have to be able to come into the limit both sides. Okay, then what Taylor says is there exists some z. There exists a z. Now this z is between a and some number x, such that this Rn of x is equal to the n plus first derivative evaluated at z divided by n plus 1 factorial times x minus a to the n plus first power. Okay. Now the reason I'm saying that z is between a and x, this is a. And this might be a minus x, like say this. If we pick the x right there, the z would be in that interval. Okay, we don't have any notation to write the interval x to a to x, like maybe if I wouldn't even know where to begin. Okay, so now this is why this is important. We have shown, okay, so before I get into the proof here, we have shown already that at the limit as n tends to infinity of x minus a to the n plus 1 divided by n plus 1 factorial is equal to 0. Okay. The reason for this is because we decided, like in this special case when a is 0, we have the sum x to the n over n factorial. This series from the ratio test converged for all x's in R. So that means that since this converged, that implied that, remember that criterion for convergence? If it's going to add up to something, then it better be going to 0. It has to be going to 0. Okay. So we have already shown this. All right. So if we can somehow bound, let's say this n plus first derivative of z by, let's say, some number m, or how about big B for bound? Okay. Then this limit, barking. We put these barking collars on them, and our dogs are just horrible. But anyways, so that's all different discussion. Okay, so if we can bound this, then that limit would go to 0. And so that would mean that the Rn of x goes to 0. And that's exactly what we want. Okay. All right. So proof here. Now I worked this whole thing through with x minus a. And, you know, now with hindsight, I probably should have just let a equal 0. Would have been easier on the eyes. Okay. But pretty sure this isn't in your textbook. All right. And some of you may one day encounter Art Moore. And Art would like to know that you have been through. He's not going to expect you, you know, to be able to prove Taylor's theorem on the spot. But Art, if you end up taking Art for 280 and 285, I mean, he gets into the Taylor series stuff for several variables, well, 2 in particular. Okay, so this stuff, you know, keeps going. Now, Taylor didn't consider that. He just considered the one variable case. Okay, so what we're going to do is we're going to fix some x. Sinus r and plus 0 g of t be equal to, now I'm not going to write down the specifics, okay, of it yet. So it's going to be the function minus the nth Taylor polynomial. Well, here, let me not do that. It looks like it looks like the Taylor polynomial, but it isn't. Okay, so this is a big mess. Okay, so it's going to be f of t plus f prime of t times x minus t, and then plus 1 over 2 factorial double prime of t x minus t squared. This is going to go all the way out to 1 over n factorial times the nth derivative evaluated at t times x minus t to the nth power. Okay. And then subtract off this r n of x times x minus t to the n plus 1 divided by x minus a to the n plus 1. Okay, now this looks kind of random, doesn't it? Now, if you go back to the mean value theorem section, And look at what that says. The proof of that, he defines this bizarre ass looking function. And you wonder, okay, well, what made him do that? Well, the reason for it was because he was taking the function and subtracting the tangent line from the function. And then that's why this funky concoction looked like, okay? For this thing, and the whole thing was to set up Rolle's theorem, okay? So what we're going to do is we're going to show that G meets the criterion for Rolle's theorem, okay? So, and remember that this Rn of x, it's not the rest of the sum, okay? What it is the difference between f of x and the nth Taylor polynomial, okay? Okay, so if I evaluate g of x, okay, then this is going to be f of x. Okay, now I'm going to put in an x everywhere I see a t. Okay, so this is going to be all of these things here that I'm underlining in red. See these all these guys are going to be 0 because x equals t. I mean, t has been assigned the value of x. Okay, so what we have is this is minus just the f of x minus, okay, now remember t is the variable here. So when I put the x in right there, I get 0. Okay, so g of x equals 0. Okay, now I'm going to look at what g of a is. It's equal to f of x. Okay, remember t is the variable. When I plug in ta for t, I get minus the nth Taylor polynomial. Okay. And then I got to subtract off the Rn of x piece. Okay. And again, when t is equal to a, these two pieces right here cancel each other out, and we just get that. Okay. So far, so good. Okay, so, well, if I kind of look at this, the f of x minus the tn of x, that's Rn of x. And I'm subtracting Rn of x, and I get 0. Okay, so we have g of x equals 0, and g of a excuse me, is differentiable. Okay, why is g differentiable? Well, each one of its pieces is differentiable. Okay, now we're going to have to take the derivative in a second, so we'll look at that again. Okay, so and it would probably impress Art enough if he asked blankly one day, anybody remember how that gets proved? And you Yeah, isn't it like we set up some function that satisfies Rolle's theorem? And he'd get so happy. So by Rolle's theorem, there exists some z, okay, now that's going to be the magic z that we're looking for, such that g prime of z must equal 0. Rolle's theorem basically said this, that if you go up and come back down, there's got to be a spot where the derivative is flat, okay? Man, 20 pitch first inning each. It's going to make it 4 innings at most. Okay, so let's look at our g prime of x, all right? I mean g prime of t. Okay, so g prime of t is going to equal negative. Okay, now remember this, the f of x piece at the beginning, that's just a function of x. Derivative with respect to t is 0. Okay, so it's going to be negative. Now I'm just going to go one by one. This is going to be f prime of t. Okay, now this next one is going to be a little bit tricky. So now we use the product rule. Okay, so it's going to be the derivative of the f prime of t, which is f double prime of t, times the x minus t, then plus the derivative of x minus t, which is minus 1, times the f prime of t. Okay, now I want you to notice something here. That guy and that guy are going to cancel. Okay, now we move on to the next one. Okay, so the next guy is going to be plus 1 over 2 factorial, and then it's going to be f triple prime at t times x minus t squared. And then it's going to be the derivative of this thing, which is going to be minus, okay, so it's going to be a 2 over the 2 factorial, then at the negative 1, and then the f double prime of t times x minus t to the first power. And these guys are going to cancel. And so notice that this guy right here is going to cancel with this guy right here. Okay. So if I do this over and over again, this is going to be plus dot, dot, dot. Okay, now plus, I'll do the second to the last step. Okay. So I'm gonna look at the n number. Okay, so it's gonna be the, what is that? Okay, so when I get to the n minus, okay, so here's what I've got written down. Negative 1 over n minus 1 factorial fn of t times x minus t to the n minus 1 plus 1 over n factorial f n plus 1 of t times x minus t to the n. Okay, so this was me taking the derivative of the last piece. okay, the n piece. So let me scroll up and show you what I just did. Okay, so it's this piece that we're doing the derivative of. So the n comes down, and that cancels and gives the n minus 1 factorial. And that's the reason for this power being n minus 1 right there. And then this second piece is now just taking the derivative of the last thing. Okay. Okay. And now we have to take that derivative of the Rn of x piece. Okay. So it's going to be minus n plus 1 Rn of x. Then it's going to be x minus t to the nth power okay, and then times the negative 1. So divided by the x minus a to the n plus 1. Remember that there's no t in there. Okay. Okay. Now we get a bunch of things that are going to be canceling here. Okay. So after you do all the canceling, here's what gets left over. We get that g prime of t is equal to negative 1 over n factorial fn plus 1 of t raised to the, whoops, x minus t, okay, to the nth power, and then plus, because of this minus, we have this Rn of x times the n plus 1 x minus t raised to the nth power divided by this x minus a to the n plus first power. Okay. And so if g prime of z is equal to 0, then that's going to imply, I'll move this to the other side of the equation, 1 over n factorial f n plus first power at z times x minus z to the nth power is going to equal Rn of x times n plus 1, and then it's going to be x minus z to the n all over x minus a to the n plus first power. Okay, so I'm going to take this equation now, and I'm going to solve it for the Rn of x. Okay. All right, so Rn of x is going to be, if I divide both sides by n plus 1, I'm going to get 1 over n plus 1 factorial. The x minus the x minus z to the n stuff, that cancels, right? Okay. And so we get f, oops, we get f n plus 1 evaluated at z times x minus a to the n plus 1. And that's exactly what we were trying to establish. Okay. All right, so just to repeat this, what Taylor's theorem says is that the big result, the thing you want to remember. Now, of course, when you see this again, you're going to be reminded of it. And in fact, you're probably going to have your professor go through the proof with you again. Okay. So there exists a z betwixt x and a, such that this Rn of x can be evaluated with just this one term, f n plus 1 evaluated at z divided by n plus 1 factorial x minus a to the n plus 1. Okay. So that is the proof of Taylor's theorem. Okay, now with this, there's some things that we can do. Okay, it's like, for example, here, let's show sine of x is analytic. Stupid word. My high school calculus book, the title was Calculus and Analytic Geometry. I don't know what the hell analytic geometry is, and I've been doing this professionally for more than half my life. And it's still like, what were they referring to? I mean, of course I could look it up on my phone, but I don't know what part of the book. You know, analytic can mean a lot of different things. Okay, so anyways, let's see. If you recall, for sine x, the Taylor series, and I just like to write T of x for the Taylor series. Let's do the Maclaurin series. N equals 0 to infinity of the nth. Well, wait, I don't have to write that down. The Taylor series is going to be -1 to the n, and then it's x to the 2n plus 1 divided by 2n plus 1 factorial. Okay, so for sine x, for this function f of x equaling sine x, no matter what derivative you use, it's just going back and forth between sine and cosine, right? Okay, so the biggest that this can possibly be is 1. Okay, so Rn of x, according to Taylor's theorem, is either the magnitude of plus or minus sine, not the magnitude, it's going to be plus or minus sine of z, or plus or minus cosine of z, right? Okay, that's what's going to be in there, divided by n plus 1 factorial x minus a to the n plus 1. The magnitude of this guy is going to be less than or equal to 1, because those things can be no bigger than 1. And then we arrive at this place again, and the limit as n tends to infinity of Rn of x equals 0, i.e. the limit as n tends to infinity of f of x minus the nth Taylor polynomial is equal to 0. So this says that f of x equals the limit as n tends to infinity of this Tn of x, okay, which is the Taylor series for the function. Okay, now that one was easy. Okay, cosine is also easy. When we start doing the e to the x stuff, this is when the bounds aren't as sharp. So like, for example here, if f of x is equal to e to the x, okay, and we want to show this is analytic. Okay, so we want to show it's analytic somewhere. Okay, so what we're going to need to do, again, Taylor's theorem, Taylor says that the Rn of x is going to be the n plus first derivative evaluated at that z, okay, and then divided by this n plus 1 factorial, and then here is going to be x minus a. In this case, we're letting a equal 0 to the n plus first power. Okay, now z is between x and 0. Okay, so the way that you kind of hem-haw around this is like this. Okay, so the x might be here, okay, or the x might be here. Z must fall between a and x. So z could be here, or z could be here. Okay, now, by the Archimedean property, Archimedean, did I spell that right? Anyone? Am I still broadcasting?
You are. I've never seen that word. So property is correct, but I don't know Archimedes.
Archimedes?
Oh, Archimedes. I mean, it's a person's name. Let me see.
So this is the Archimedean property. It's kind of a,
the I instead of E, it's ARCHI.
okay.
Otherwise, it's right. ARCHI M.
Median. Okay. There exists a counting number n such that n is bigger than e to the z. Okay, so it's kind of like it's pointing out the obvious, right? And so I mean, not that. I meant n is bigger than z. So that means that e to the z is less than this e to the n. Now that number is fixed. Remember, the z was fixed. I mean, it's, well, not fixed, but it's like in between 0 and x, okay? And so because of this, we can say that the Rn of x in magnitude is less than or equal to this number, e to the n, times x to the n plus 1, all over n plus 1 factorial. And the limit as n tends to infinity of this Rn of x equals 0. So that means e to the x equals its Taylor series, or its Maclaurin series. Okay. Now I have seen people do this. My buddy Tim Shemp, I wonder whatever happened to him. He and I were math majors together, and he was a tutor working for me in the tutoring lab. I started working in the tutoring center. My boss, Lara, I just decided one day that I should be in charge. And so she said, okay. And then eventually I started working for the dean. And I mean, I gamed the shit out of college, man. I mean, I had a faculty parking spot. All my books I ordered through the math department. I had a master key to the whole building. I mean,
Cal Poly?
Yeah, Cal Poly Pomona. So that's how I did it. If you think about it, I've only spent 15 months out of my life out of school. I mean, you don't count being a baby, but I went to college, I went to grad school, got a job for 15 months. I hated it, went back to grad school and got this job intending on going back to grad school. And then we started having babies. Bellinger popped them up. And so anyways, so my advice for where you're going to be using this in the real world is just relying on what my professors had been telling me way back in the day. Many of you are going to have to take a numerical analysis course. I've been telling you guys this for a while, for you engineering majors, okay? And Eduardo, you're going to have to take the numerical course, with the math department. Now, you can either do it with the engineering department and you're going to be crunching numbers and shit like that, or you take it with the math department and it's all proving that this kind of stuff works. And it was in this class where it was basically just numerical analysis. It was 2 quarters, 401 and 402. And they were just nothing but applications of Taylor series. And this is how I got good with Taylor series stuff. So Tim, and this class was so easy, we would have, I told you this, we'd have contests to see who could be the least prepared for the exam. And Tim won once, we put $5 in a jar, a bunch of us, And on the day before the exam was Tim's birthday. So on Denny's, you get a free meal on your birthday. And him and John Jasminzek, who's a now physics professor at Cal Poly San Luis Obispo, they drove around to 47 Denny's in the greater Pomona Covina area. And he won easily, as you know. Like, what'd you do? I watched all 3 Star Wars. Back then, there was only 3 Star Wars. I watched all 3 Star Wars and drank a case of beer. Okay, well, yeah, Tim wins. So anyways, what we used to do with this stuff is stuff like you can do stuff like this. The sine of x is equal to e to the ix minus e to the negative ix over 2. This comes from Euler's formula, okay? And it turns out that the cosine of x is equal to e to the ix plus e to the negative ix divided by 2. Either today or tomorrow, I'm actually going to be able to prove Euler's formula. As a matter of fact, maybe we should do that next, okay? So anyways, what Tim and I would do is we would run e to the ix into this. The sum, n equaling 0 to infinity. Now it's going to be ix to the n over n factorial. You know, we would plug bizarre things into the series, and we challenge each other to try to back out of it. You know, we have this series up here. We showed that the sine, this is the sine guy. So we would figure out what the sine of like an imaginary, and if you plugged in I into this series, what would it look like? Okay, so let's do this. Let's look at Euler's formula. Okay, so if I start enumerating this stuff, e to the ix, okay, when n is 0, it's going to be a 1, and then when n is 1, it's going to be an I times an x over a 1. When n is 2, it's going to be I squared, which is negative 1 x squared over 2 factorial. Okay, now when when n is 3, I cubed is negative I. So that's going to be minus I x cubed over 3 factorial. When n is 4, I to the 4th is 1. So I'm going to get x to the 4th over 4 factorial. Okay, now I to the 5th is the same as I. So now that's going to be I x to the 5th over 5 factorial. I to the 6th is the same as I squared. That's negative 1. So that's going to be x to the 6th over 6 factorial. I to the 7th is the same as I cubed, which is negative I, x to the 7 over 7 factorial. I to the 8th is 1, x to the 8th, 8 factorial, minus plus, and this keeps going. Okay, now, this series right here is absolutely convergent. Now that's my phone thinking of
Where would you like to go?
That's my Siri.
Sorry, I didn't quite get that. I'd be happy to give you directions. Where would you like to go?
For some reason I like that Indian accent. Hello. You ever see that episode of The Simpsons where Bart goes into the convenience store and makes that massive ice cream cone, and what's the guy's name? Abu? Your gargantuan cunt is making a mockery of our self-serve policies.
Yeah, and they, I don't know if you followed it, but they recently got rid of that actor, Hank Azaria.
Oh yeah.
Long time he was on the show.
Yeah, some Padre just hit a home run. Yeah, pretty flat slider. Okay. All right. Because this series is absolutely convergent, we can manipulate it. So if we take all the real stuff and collect it together, we're going to get 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial plus minus ... If you collect all the I stuff up, I'm going to get an x minus x cubed over 3 factorial plus an x to the 5th over 5 factorial minus x to the 7 over 7 factorial plus minus ... And we just proved that the sine was analytic. Same proof goes through for cosine being analytic. So this is the cosine of x plus I times the sine of x. Okay, so we have now finally proven Euler's formula. E to the I theta is cosine of theta plus I times the sine of theta. All right, now the first time you may have seen this would have been in pre-calculus. Okay, and in pre-calculus, when we're trying to like take square roots of complex numbers, we have to use, we kind of need to use this. Okay, now when we get to math 285, and you guys can all take 285 in the fall after you pass this class, the prerequisite for 285 is just 185. There's only one topic in 285 that requires any knowledge of material from math 280, and it just has to do with partial derivatives and things which are called exact differential equations. Matter of fact, I'm going to cover exact differential equations for you, even though it's not in the textbook, just so you'll, for you guys that are going to 280, you're going to do something in 280 that is exactly the same, just different terms get used, different words get used in the process. Okay.
Bobby, is 285 linear algebra?
Yeah, differential equations and linear algebra.
Are you teaching that this fall?
I am currently not teaching it in the fall.
Okay.
I just have the 2 classes. The reason for that was I was supposed to be coaching on the freshman staff at the high school for the freshman team for football. So I cleared my schedule and done that. Now, art has a 285 in the fall. And no one's heard from Art in a while. So he might just keep doing this, or he might just give up, or I don't know. So there's a 50-50 shot that I would be taking his class. 50-50. So we have to see about that, but that'd be an emergency. Okay, so here we go. This is Euler's formula. Now, he did all this, of course, in his head. Even though he was blind for the last like 30 years of his life. Can you imagine doing math blind? Just close your eyes and try to work out equations and stuff. I was in grad school with this Brazilian guy named John, and he was a competitive swimmer when he was a kid. And something happened. He lost all his eyesight, just completely blind. But he was in grad school with us at UC Irvine, and man, the brain power that guy must possess. Just you'd almost see the smoke coming off of his head when he was thinking through stuff. Okay, so now we own Euler's formula. So there you go. Okay, now figuring out other guys, let's find the Taylor series for, let's say, f of x. Let me see here. Which one am I doing here? Da-da-da-da-da. Let's do the Taylor series for the cube root function. Okay. Okay, so let's do this at a equal 1. Okay. And we start taking derivatives, it's the exponent goes negative, and so we can't be putting a 0 in, or just we have to stay away from 0. Okay, so f of 1 is equal to 1. F prime of x is 1/3 x to the negative 2/3. F prime at 1 is just going to be this 1/3. F double prime of x is going to be -2 divided by 3 squared times x to the negative 5/3 power. And f double prime at 1 is going to be -2 over 3 squared. F triple prime of x is going to be positive now 2 times 5 divided by 3 cubed times x to the negative 8/3. And f double prime, or f triple prime at, wait, I'm watching the stupid game. Let me switch it to the angel game. Why watch a good team like the Dodgers? Why can't I watch a shit show like the Angels? Okay, so f triple prime at 1 then is just going to be this number 1, 2 times 5 over 3 cubed. Now to get the pattern, I generally go out 5 times. -2, 5, 8 over 3 to the 4th. Oh, Trout's back in the lineup. Let's see. Everybody stops their life when Trout's at bat. X to the negative 11/3, and f for derivatives evaluated at 1 is going to be -2, 5, 8 over 3 to the 4th. Okay. So do we want to take a stab at what the nth derivative is going to look like? Let's leave a little room in between there and see what it's going to be. The nth derivative evaluated at 1, it's going to be -1. It's going to alternate back and forth. Okay, so notice that it's negative when it's even, when the derivative is even. So we're going to have to do that. And then it's going to be 2 times 5. Oh, Trout home run. Nice. 2 times 5 times 8. Okay, now this is where you just you kind of throw a guess in. And then this is going to be obviously 3 to the n. Okay. Okay, so we're counting by threes starting at 2. Okay, so how about we do 3n minus 1. Okay, so when n is 4, we have to get the last thing as an 8. Okay, so when n is 4, I think if we do, when n is 4, I need 8. So if I do 3n minus 5, does that work? 12 minus 5, no, 3n minus 4. Okay, so when n is 4, this last term has to be 8. Okay, now the fifth derivative, evaluated at 1, is going to go 2, 5, 8, 11 over 3 to the 5th. Okay, so when n is 5, I need 11, and it looks like it works. Okay, now you have to figure out where the pattern starts. Okay, so when n is 0, we can't account for that here. Okay, so the Taylor series, the t of x, is going to be the first guy, which is a 1. Okay, now the second term is still positive. Okay, so when n is 1, it's not working, because when n is 1, right here, that's going to give me a 2. So that's going to be positive. N is 1 giving me a negative. So the whole thing would be negative. And the second derivative is positive. So you manually have to put in that second term, 1/3 times x minus 1 to the first power. Now let's see if the pattern starts. Okay. When n is 2, it's going to have to be negative, and it's going to be just the 2. So it looks like it's working. So plus the sum. Now, by the way, kids, if you neglect to do this, you get problems wrong. Okay, I'm going to be pretty harsh with this. Okay. So n equaling 2 to infinity, -1 to the n plus 1, 2, 5, 8, 3n minus 4, divided by 3 to the nth power, x minus 1 to the n. Okay. Now, if you look at this piece right here, this is the linearization of the cube rooting function evaluated at 1. Okay, and as it said after that section in that discussion about Taylor polynomials, that's just the first level approximation. Okay. All right. So is this thing analytic? So this is where stuff starts to get hard. Okay. Bounding these things. So the n plus first derivative f n plus first derivative evaluated at x is going to be this -1 to the n now plus 2. And then it's going to go 2, 5, 3n minus 4. Then the next one up would be 3n minus 1 divided by 3 to the n plus first power. Okay, so the magnitude of this thing, and this is where I remember doing most of these arguments, was in the numerical analysis course. The magnitude of this is going to be this weird counting by threes factorial function. And I forgot the power of x here. X minus 1. Now, what was I doing? It's not x minus 1. It's x to the n plus first power. And evaluated it. Well, I guess I need to, I'd have to have a general expression for this guy. So it's not this. It's x to some power. Now remember, we're counting by threes here. So it's going to be 3n plus 2 divided by the 3. Okay. So the magnitude of this thing can be this big, 3n minus 4. Now here's the next one, 3n minus 1 divided by 3 to the n plus 1. And all of these exponents are negative. And so that's going to be x down in the downstairs to the 3n plus 2 over 3. And so the magnitude of this guy evaluated at z, where z is between 1 and x. Okay, so where here's 1. Okay, x could be here or x could be there, as long as it stays away from the 0. So that means that the z is either going to be there or there. Okay, but anyways, the magnitude of this thing is then going to be 2, 5, 3n minus 4, 3n minus 1 divided by 3 to the n plus 1, z to the 3n plus 2 over 3. Absolute value. Okay. All right. So is there any obvious bound on this thing? The thing that I'm looking at right here is what's in the denominator. Okay. So bounding these derivatives, it's not a trivial thing to do. Okay. So turns out that this is an okay expansion to use. However, what we want to do is we want to go like here's the A is 1, and then here's some 1 minus R to some 1 plus R. Okay. Now we want this R to stay away from the 0. Okay. And I think if we make sure that the Z is bigger than 1, if Z is bigger than 1, 1 over Z is less than 1 over 1 or less than 1. Okay. So as long as we're getting values over here, we can say that this is less than or equal to 2, 5, 3n minus 4, 3n minus 1 divided by 3 to the n plus 1. Doesn't matter what this exponent is because that 1 over z number is less than 1. Okay, now here's where we start running into problems. Okay, the bound that we just used wasn't sharp enough because each one of these terms up here is eventually bigger than 3. And so if I take and if I write it like this, 2, 5, 8, there's n plus 1 terms here. And if you put the 3s, 3, 3, 3, this limit's going to go to infinity. Okay. So you need a sharper bound on this. Now, this is not the kind of thing where I'm taking this class. This is more going to be for a few of you, the physics and Eduardo and anybody else that's just kind of interested in it. Okay. So let's do a computation and let's see. Okay, so let's, for example, let's use T3 of x to approximate the cube root of, let's say, 2. Okay, so 2 is kind of close to 1 and 1 has an easy cube root. Okay, so T3 of x is equal to, if you go back, we had to manually put in the first couple terms. Okay, then when the counter started, way back up here, where did I put my final series? When n is 2, it's going to be minus 2 over 9 x minus 1 squared. And then when n is 2, gotta go all the way back up here. It's gonna, I mean, when n, wait. When n is 1, this was the n equals 2, right? The n equals 2 was that one. And so now the 3, when n is 3, it's going to go 2 times 5 over 9. It's going to be plus 2 times 5, which is 10 over 9 x minus 1 cubed. Okay. Now the whole idea around this is that this is easily computable. Let's see, it's going to be 1 plus 1/3 minus 2/9 plus 10 over 9. So that's going to be 4/3 minus 8 over 9, which is 12 minus 8 over 9, which is 4 over 9. And then those old timers would long divide. Okay. Back in the days of, hold on a second. Geez, my buddy's just got home from the hospital. Okay. So on the calculator, you know, we could actually long divide this too. 4 over, yeah, that can't be right. This is, that's a plus. That's a plus. Yeah. So that's going to be 20 over 9. I could tell nobody's paying attention now. So 20 over 9, clear. 20 divided by 9 is we get 2.22. Okay. And the cube root of 2 on the calculator says the cube root of 2 is equal to 1.25. So obviously I've done something wrong here. So what am I doing wrong? Let's see. Start over. When in doubt, approximating the cube root of 2. Okay, so I write my series down again. 1 plus 1/3 T3 of x, 1 plus 1/3 of x minus 1. And then this 2 is going to be minus 2 over 9. Oh, minus 2 over 9 x minus 1 squared. And then plus 2 times 5. Oh, I know what I did wrong. It's 27 down here. X minus 1 cubed. Okay. So now I really know nobody's paying attention. So T of 2. Oh, got it. So T of 2 is 1 plus 1/3 minus 2/9 plus 10 over 27. Okay, so it's 4/3 minus 6 over 27 plus 10 over 27.
Getting 40 over 27.
Is that what we're getting?
I mean, that's
I'm
what
getting
I
4
40 over 27.
4 over 3 plus 16. No, 4 over 27.
Yeah, so you times 9 by, or 4 by 9, that's 36. The 36 plus 4, that's 40 over 27.
Right. 9, 36, 40 over 27. And 40 divided by 27 equals 1.48.
Is that the same as what the cube root of 2 is? I don't have a calculator on me. So.
No, it's pretty bad. 1.48.
And what's the cube root of 2? I don't have a calculator near me. So.
The cube root of 2 is 2 cube root 1.25. Okay, so let's go out another term. Okay, T4 of 2 is going to be 1 plus 1/3 minus 2 over 9 plus 10 over 27, then minus, okay, now this is going to be 81, and then that's going to be 2 times 5 times 8, right?
2 times 4 times 8, like 40?
Well, that's the next one, right?
Or sorry, that would be 80 if it's 2 times 5 times 8.
Yep. Okay, so we know that this is 40 over 27 minus
minus 80 over 81.
80 over,
That'd be 120 minus 80, so it's 40 over 81 is the answer.
3.
Oh, yeah, 40 over 80, or yeah, 40 over 81, the answer.
Really?
I mean, that's what I'm getting, because 3 times 27 is 81, and 3 times 40 is 120. 120 minus 80 is 40, so 40 over 81. Could be wrong, but sounds right
Yeah,
to me.
this approximation is just, it's not very good, as you can
Better
see.
and better and better. Everybody can see it's great.
Well, this one at least was in the ballpark. Notice what happens if you take, so if you take 40 over 27, and then you subtract 80 over 81, you get 0.49. Okay, so this thing really isn't working very well, to the point where I'm like wondering if we actually have this correct. But I'm pretty sure we do.
Just throw that calculator away, man. That's the easy way. This is what the cube root of 2 is now. 0.49. Done.
So let's look at T1 of X. T1 of X that's just the linear approximation, right? That's 1 plus 1/3 of X minus 1. So T1 of 2 is going to be 4/3, which is 1.33, forever and ever. And the number that we're looking for is something around 1.2-ish, 5, something like that. And then the T2 of X, 1 plus the 1/3. Oh, duh. This is where I fucked up.
Fook just said maybe you missed the n factorial for the series.
Yep, that's what I did. I got so worked up with the bounding. Okay, there's the n factorial there. Okay, now this helps. Now this is going to be n plus 1 factorial all the way back up here. See, now if we were a normal class, one of you would have shouted out, Bobby, you forgot the factorial. So then this is going to be the n plus 1 factorial. And then this bound here will then be n plus 1 factorial. Okay. So I guess one could take each one of these n plus 1 factorials and like put them here, and then then an n, and then an n minus 1. That's the kind of thing you'd have to be bounding. Okay, now if I readdress this guy here, okay, this I forgot the 3 factorial. This guy, I forgot the 2 factorial. Okay. And so this is going to be a 2 factorial. This is going to be a 3 factorial. So let me just erase this shit. Okay, so this is going to be, well, it drops up again. Here we go. And he gets ball hard. Okay, so it's going to be 4 thirds minus 1/9 plus 10 over 27 times 3 times 2. So that's going to be a 5 over an 81. That's probably better. Okay, so now let's calculator that fella and get 4 thirds minus 1/9 plus 5 over 81. And I get 1.28395 dot dot dot. Okay. Now just to see this in action here, let's look at what T4 would be. Okay, now this time it's still going to be this 4 thirds minus 1/9 plus 5 over 81. Then it's going to be minus, okay, now the multiplication goes up to 8, right? So it's going to be 258. 2 times 5 times 8 divided by 3 to the 4th power 4 factorial. Okay. And so let's see here. They walked in. So I'm going to say that's going to be 80 divided by 81 equals divided by 4 factorial equals, okay, so this, and added to the previous thing, 4 thirds 4 over 3 minus 1 over 9 plus 5 over 81. Now I'm doing something wrong here. That last term, so it's ten times 8 is 80. 80 divided by 81 divided by 4. It keeps giving me an error. I'm not plugging something in right. Okay, 80 divided by 81 equals, divide that by 4 factorial equals. Okay, so that number plus 4 over 3 equals minus 1 over 9 equals plus 5 over 81 equals 1.32. So we moved away from it, as long as I did this correctly. Did I do that wrong? I'm going to continually scroll back up. So T4, I needed 4, 2, with the 3. 3 gives me the 5. the 4 gives me the 8. So, yeah.
When you plug it all into the calculator, it comes out to 1.242798.
Yeah.
Blah 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 all the way.
I didn't correct. Let's just write it all out. Okay. So I need to write the Taylor series again. Okay, T of X is equal to 1 plus 1/3 X minus 1. And then we could start the sum, right? N equaling 2 to infinity, -1. It starts off negative, so we got to do that. 2, 5, 8, all the way out to 3n minus 4, 3 to the n factorial. Anytime I make a mistake with these things, it's always the factorial. X minus 1 to the nth power. Okay, so T4 of X, 1 plus 1/3 of X minus 1 minus 2 over 9 times 2 X minus 1 squared plus 2. That's the problem. See, I'm using 4 here where T4 is only going to go up to the 4th power. So it's 2, 5. No, I got this right. What I'm doing is I'm missing a term. Divided by, this was the n equals 0, 1, n equals 2. There's a chancellor's office system webinar. That might be a thing that you were talking about. Plus 2 times 5 divided by 3 cubed times 3 factorial, X minus 1 cubed, and then minus 2, 5, 8 over 3 to the 4th, 4 factorial, X minus 1 to the 4th power. Okay, so T4 of 2. Now, if I get this fucked up, I'm quitting. Minus 1 over 9 plus 10 over 27 times 6 minus 80 over 81 times 4 times 3 times 2. 4 factorial is 24. 4 times 3 is 12 times 2 is that. Okay. Now, there we go again. I'm going to I'll start off with 4/3. Okay. Then I'm going to subtract off 1/9. And then I'm going to add 10 divided by, what's 27 times 6? 120, 162?
Yeah.
Over 162 minus then the quantity 80 over 81 over 24, close the bracket, equals. So this is what I get, 1.2427983. You get something similar? Somebody?
Yeah,
That's what-
I got the same thing.
Okay. All right, now let's look at this remainder business, okay? R4 of X in magnitude is going to be the fifth derivative evaluated at Z, then Taylor's theorem says it's going to be X minus 1 to the n plus 1. So in this case, it would be the fifth power divided by 5 factorial. Okay. If I plug in a 2 into this, R4 of 2 is equal to the fifth derivative evaluated at some Z divided by 5 factorial. Okay, so what is the fifth derivative? The fourth, well, let's see. Maybe we should just do it again. So F is X to the 1/3. Prime is 1/3 X to the negative 2/3. Double prime is negative 2 over 3 squared X negative 5/3. Triple prime, knee's starting to hurt. Triple prime is going to be 2 times 5, 3 cubed, X negative 8/3. 4 derivatives is going to be negative 2, 5, 8 over 3 to the 4th, X to the negative 11/3. Okay. And so this is going to be the magnitude of 2 times 5 times 8 times 11 divided by divided by 3 to the 5th power, and then 5 factorial times, let me erase part of this line right here. Okay, now the Z is now going to be raised to the negative 14 over 3 power. Okay. Which we can write as 2, 5, 8, 11, 3 to the 5th, 5 factorial times Z to the 14 over 3. Okay, now Z is between 1 and X. Okay, in this case, the X is 2. Okay, and so the Z is somewhere in here. So Z is bigger than 1. This means that 1 over Z is less than 1. Okay, so this can be no bigger than 2 times 5 times 8 times 11, 3 to the 5th, 5 factorial. Okay, so let's compute that number. So this time I'm going to do it differently. Okay, I'm going to start off with 5 factorial. 5 factorial times 3 to the 5th. 5 factorial times 8 to the 5th. 8 to the 5th. 5 factorial. 5 factorial times 11 to the 5th. 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 11 to times 3 to the 5th power equals, then I'll flip that number over and multiply times 2 times 5 times 8 times 11 equals. So this number, which is Rn of 2, is approximately less than or equal to 0.3017836 blah, 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 blah. Okay. Now our answer is still up here. It's the 1.24. So if I take the cube root of 2 and I subtract off the 1.2427983 ish number, let me do 2 cube root minus 1.2427983 equals roughly 0.01722, and that's certainly smaller than 0.03. Okay. Okay, so what I think you should be doing with this stuff, for those of you that are in medical school path trajectory, this is probably not something that you'll investigate again. Excuse me. But for you guys that are engineering majors, you will be seeing this stuff again. So let me stop the screen sharing. Okay, so let's see how many people stayed here tonight. Participants, I got 30. How about chat? Maybe you missed the n factorial. Yeah. So let's see. Let me go through the chat. Anything specifically for me? Let's see. Announce the next test. It's going to be Tuesday. Okay, Tuesday we'll do the test, and it's going to be part 2. And then I'll also post the 5th one that same day. That's not due till the day of the final. The final would be the last day of class, and it's going to be just like this normal final exam. Most of you don't have to take it because most of you have an A. Now, like I said, this next test, you might not dig up the technology. A lot of times when they ask for series and you plug it into like something, it'll give you like the first 5 terms and that's it. You need to have like the whole thing. Okay. I am going to try to cook up some kind of a remainder question for what, the problem, because I want you guys to at least have some experience playing with it. You don't have to get worried. You're gonna, you'll figure it out. You guys all can work with each other and stuff, look in books. Okay. But definitely gonna have one. If Albert goes yard, he ties big knave. So anyway, so on Tuesday, yes, I am. Chat 2. So on Tuesday, we're posting. Now, on Tuesday, I'm posting part 2 of the chapter 11 test, which is going to be, like another 8 questions or so. Okay. And then I'm going to give you test number 5. Test number 5 is due on the day of the final. I'm trying to treat this like a normal class. So, and then on Thursday night of next week, then it'll be due at 6 o'clock, and then I'll make the final exam available, and you guys will just take the final for those of you that are going to. Okay? That sound good?
Yep.
All right. All right, so I've got to take some stuff down to my wife at the beach.
Professor?
Yeah.
So will the part 2 be due, will it be a time test?
Yeah, it'll be another one of those time tests.
Okay.
All right. So I think we finish with that. All right. So I need to, like I said, I got to take the e-bikes down to my wife at the beach.
What? I'm fine at the beach, man. Are you guys staying there, or are you just chilling for the night?
My wife rented a place down there,
Yeah.
and the little kids are down there right now. The older boys work.
Oh, okay.
And then she doesn't work for she basically has 2 weeks off. So she's got lined up her friends coming over and stuff like that. I'm staying here.
Hey, when does OCC's fall semester technically start? Does anyone know? I really haven't been paying attention much to.
24th.
Oh, okay. So we have like 2 weeks between.
24th.
Okay.
You know, we get a week off, and then
Oh, well, it's only a week off? Let me see. We
maybe it starts on the 31st.
Jeez.
I'd have to look on the
Hmm.
I'd have to look on the thing. Okay. All right. Well, my wife says it's the parking spot they have down there is small, and my Raptor is huge. So I think I might have to put the bike rack on her bike or something. I mean, on her car. All right. So you guys working those problems. Some of those problems in the last section are kind of challenging. The bounding, the error and stuff like that. Okay. So you have full-blown Taylor result there. And, you know, dig around in other, places.
All right.
Sound good?
Sounds good.
All right, man. See everybody tomorrow.
Peace. See you guys.
Bye.